In this last lesson of our course, I'd like to utilize some of the counting strategies that we've developed in the last few lessons to answer some questions in elementary probability. But before I can do so, we need to define a few terms that are going to come up throughout this lesson. So first, let's define something called the sample space. The sample space is the set of all possible outcomes for a particular activity or experiment. And each element of the sample space is going to be called an outcome. So, for example, if the activity in question was just to flip a coin one time, then the sample space would just be the set with an H and a T in it, where H would stand for getting a heads and T would stand for getting a tails. Similarly, if the experiment was rolling two number cubes or dice and looking at the sum of those two faces, then the sample space would be the set of numbers from 2 up to 12, because these are the possible sums that you can get. The 2 is the smallest from 1 plus 1, and the 12 is the largest from adding 6 and 6. Now, from here, we can then define the theoretical probability of an event. So here's that definition. If a sample space has n equally likely outcomes, and an event, let's call it A, occurs in m of those outcomes, then the theoretical probability of event A is denoted by little p of A, and it's given by p of A equals m divided by n. Now, just to get the idea of what's really going on with these probabilities, let's just do a few basic examples to make sure the terminology makes sense. First of all, find the theoretical probability of getting an odd number when you roll one number cube or one die. Now, in this case, when you're just rolling one of these, the sample space is the set of numbers from 1 to 6. 1, 2, 3, 4, 5, 6. So in that formula we had just a moment ago for probability, we had a fraction m divided by n, and that denominator is going to be 6 in this case. That would be the value of n, because we have 6 elements in the full sample space. Now, the next question we have to ask is, how do we get the numerator of that probability? And in order to answer that, we have to ask this question. How many of the outcomes in that sample space give us what we want, which is an odd number? Well, the outcomes we would want in this case would be the 1, the 3, or the 5. And there's 3 numbers there, 1, 3, and 5. So the m in this formula is going to equal 3. That's the numerator in this probability fraction. And therefore, for this example, the theoretical probability would be 3 divided by 6, which is the same as 1/2. Now, I hope that actually makes sense to you, sort of common sense, because half of the outcomes in the sample space are odd, and the other half are even. So hopefully we would get the theoretical probability of 1/2 if what we're trying to have as an outcome is an odd number. Now, given that we've done that example and we feel okay with it, why don't you try the following problem on your own and see how you do? What is the probability of randomly selecting a prime number from the first 20 positive integers? Remember, the probability of that event is going to be m over n. Now, what's the sample space in this problem? You know, you actually have to figure out what the sort of large space is of all possibilities before you can ever move forward with one of these problems. And the size of the sample space is the denominator of that theoretical probability formula. So we need to know what the set of numbers is that we're choosing from. In this case, the sample space is all the positive integers from 1 up to 20. So 1, 2, 3, and so on up to 20. That means that there are 20 numbers in the sample space, so n, the denominator in our probability, is 20. Next, how many elements in the sample space are the ones we want? In other words, how many of them are prime? That's the question here. Well, remember, the prime numbers are going to be the numbers whose only divisors are themselves and 1. So, for example, 2 is a prime, 3, 5, 7, 11, 13, 17, and 19. Those are the primes in the set from 1 to 20. And now you need to ask yourself, how many numbers are in that little set? We had 2, 3, 5, 7, 11, 13, 17, and 19. Well, there are 8 of those. And so m, or the numerator in my probability, is going to be 8. And therefore, the probability of selecting a random prime number out of the set of numbers from 1 to 20 is equal to 8 divided by 20, which I can reduce down to 2/5 after I simplify that fraction. Now, let's try one more example of this kind just to make sure that we're settled on it. And this time, we might have to bring in some material on permutations and combinations. We'll see. Here's the example. A jar contains 70 red marbles, 25 white marbles, and 5 blue marbles. You plan to choose one marble at random from the jar. So you're just going to close your eyes and reach into the jar and pull out a marble. What's the probability that you choose a white marble? Now, and then I would like to ask, what's the probability that you choose a marble that's not blue? So we're actually asking 2 questions here. Probability of choosing a white marble, and then probability of choosing a marble that's not blue. Now, how many possibilities are there, so to speak, in my sample space? Well, the sample space is now the selection of each of those different marbles, just one at a time. So there's 100 different possibilities here just from choosing one marble out of the total 100 marbles. So the denominator of my probability formula is 100. Now, there are 25 marbles in the jar. We were told that. So there are 25 different marbles that we would want to select in the jar for this first experiment of choosing a white marble. And therefore, the numerator for that problem is going to be m equals 25. So the probability of choosing a white marble out of this jar at random is going to be 25 divided by 100, which is 1/4. Now, what about that other question? How do we find the probability that we randomly select a marble that is not blue? Well, the probability of not blue is the same as the marble being either red or white. We only had 3 colors of marbles here, red, white, and blue. And the number of ways of getting either a red marble or a white marble is 95. And so the total number of ways that we could successfully actually do the experiment, if you want to think of it that way, is m equals 95. And therefore, the probability of selecting a marble that's not blue and doing so at random is going to be 95 over 100, which is the same as 19 over 20. Now, in that example, we didn't have to use combinations and permutations, but we're going to use them a lot more as we move forward and get some slightly more complicated examples. The cool thing is that they're so helpful, these combinations and permutations from the previous lesson, for counting things intelligently and counting them quickly. So let's look for those now as we move forward in other examples in the rest of this lesson. Let's move to this example. When you're dialing a phone at your local school campus, you only have to use the last 4 digits of the phone number to dial the number. This happens at some businesses as well, where you only have to use, say, the last 3 or 4 digits. In this case, we have to use the last 4 digits, and they could be anything from 0000 to 9999. Now here's the question. What's the probability that you dial a 4-digit number at random where all the digits are different? So you randomly are selecting your 4 digits, if you will, and you want to know what the probability is that as you choose those 4 digits at random, that the digits are all different. Now, let's peel this problem apart a little bit at a time so that it doesn't feel so big to us. First of all, what is the sample space, if you will, in this problem? I need to know the size of the sample space because that's going to give me the denominator of my probability. Well, I was told in the problem that I could have any of the numbers from 0000 up to 9999. That means the numbers start at 0, 0, 0, 0, then the next one could be 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, and they could go on for a long time until I get up to, say, 9997, 9998, and 9999. Now, that's the sample space. Remember, not everything in the sample space is going to be what you want, but that's the set of all the possible 4-digit numbers you could have. How many numbers are in that set? Well, the answer is that there are 10,000 of them. And that might be a little confusing. You might have wanted to say that there were 9,999 of them. But remember, we've not started the numbers at 0001. We started at 0000. And when you do that, you actually will have 10,000 different 4-digit numbers that you could have. So the size of my sample space is 10,000. And that means the denominator in this probability question is 10,000. Good. Now, let's move forward then and think about the numerator as we're working through what's happening in this probability question. Now, think about what we want to do. We want to ask how many of the numbers in this sample space are going to have distinct digits. So what I've got then is a question of 4 different blanks and filling in those 4 blanks with different digits. That feels quite a bit like the previous lesson that we were working with, where we were trying to fill in these kinds of blanks. Now, I'm trying to fill in these blanks with different digits. How many ways can I do that? Well, since the digits are allowed to be anything from 0 to 9, the first blank is allowed to have 10 different possibilities. So the first blank has 10 choices. Now, the second digit then, because it has to be because it has to be different, only has 9 different choices for that second blank. So I have 10 choices for the first, I have 9 choices for the second, and now I want to look at the third blank. And in that case, I'm going to have 8 different possibilities for the third blank. And finally, I would have 7 different possibilities for the fourth blank. Now, if you think about it for just a second, that means that the total number of different possible 4-digit numbers that we want to have with distinct digits is going to be 10 times 9 times 8 times 7. And that, by the way, is one of those p-values that we saw in the previous lesson. So the numerator of my probability, which is the total number of the 4-digit numbers that I want, is going to just be p of 10, 4, because we want permutations here, right? Because the numbers and their orders matter. So the numerator of this probability is p of 10, 4, which is 10 times 9 times 8 times 7. And that, by the way, is 5,040. Now, I now know everything I need to know about the probability that I was asked for in this problem. It turns out that the probability of just sort of randomly getting a 4-digit phone number, which has all different digits, is actually 5,040 divided by 10,000, which is, if you reduce just a bit, 63 divided by 125. And let me just make a comment to you really quickly. I don't know if you paused when we started this example to think to yourself, I wonder how big that probability is going to be. But notice that this probability is just barely bigger than 1/2. I think it's pretty cool, actually, that this probability landed right near 1/2. I don't know if your intuition told you where it would be, whether it would be 1/10 or 1/2 or 3/4 or whatever. But it's really interesting to see here that the probability of randomly getting a phone number which has different digits is extremely close to 1/2. Now, for the rest of this lesson, I'd actually like to use examples that relate to a deck of 52 playing cards, the kind of deck that's often used in something like poker or a similar card game. Now, if you're not familiar with a deck of 52 cards that are used in something like a poker game, then I might suggest you actually get a deck of these cards and just stare at them for a while so that it makes sense to you what I'm about to say. The ideas of how many cards there are, how many of each type, how many are red, how many are black, and so on. So you may want to actually go out and grab a deck of 52 cards just to get used to the kinds of things we're going to talk about. Now, as a quick reminder, the standard deck of 52 playing cards that's used in games like poker contains 4 suits. And the suits are the spades, the clubs, the hearts, and the diamonds. And in each suit, you have 13 cards. And these are the cards that are numbered from 2 up to 10, along with a jack, a queen, a king, and an ace. Now, using such a deck without any of the jokers included, we want to throw the jokers away, they would really mess up these problems. Otherwise, let's work out several different probability questions. And again, it might help you to actually have a deck with you if you're not really used to the standard deck of 52 playing cards. So here's the first probability question I would ask you related to such a standard deck. What is the probability that you draw one card at random from the standard deck of 52 cards, and that one card that you draw is a red king? Okay, that's the question. What's the probability that you draw a red king at random from a 52 card deck? Well, the first question you should ask yourself is, let's see, I've got to find a probability. I need to get 2 numbers. And I would suggest, believe it or not, that the first number you try to get is that denominator, which means you need to ask yourself, what is the sample space of this event or this experiment that I'm doing? Well, notice what you're doing. You're actually just drawing one card out of a 52 card deck and then looking at it to see what it is. In this case then, the sample space just has 52 possible outcomes in it. Basically, one outcome for each card. You could pull out an ace of spades, you could pull out a 3 of diamonds, and so on, and each of those would be an element of the sample space. So in this example, the size of the sample space is 52, which means the denominator of your probability is also going to be 52. Now you're ready to think about the desired outcomes. In other words, the actual events that you want to really have happen in this case. And in this case, you want to have a red king be one of the cards that you pull out, or be the card that you pull out. So how many ways could you have a red king in this deck? Well, the answer is there are exactly 2 red kings in the deck. One is the king of hearts, and the other is the king of diamonds. And those are the only 2 desired outcomes that you would want, which means the numerator of your probability is just the number 2. You only have 2 cards that you really want to have come out as you do this experiment. And therefore, the probability of randomly selecting this red king from the deck is exactly 2 divided by 52, which is the same as 1 over 26. Okay, let's try another example. And now the example is going to get a little bit bigger as we think about what our sample space is. What is the probability that a 5-card hand is dealt to you which contains only black cards? Now, I have to be honest, this example contains some pretty big numbers. So it may feel a little overwhelming to start thinking about the size of the sample space, for example. But just stay patient. I think you'll be okay as we work through the example. Let's first talk about the size of the sample space. And to do so, let me just clarify what I'm saying. I have my deck of 52 cards, and I'm just going to deal 5 cards to you. So I'm not worried about doing anything beyond just handing you 5 of those 52 cards, and I want to see if they're all that same color. In this case, then, the sample space is going to be the set of all possible 5-card hands that you could have dealt to you at random. Now, how many different ways could you have 5 cards given to you at random out of a deck of 52? Well, this is a combinations question. And by the way, it's not a permutations question because the order in which the cards are handed to you does not matter. You only care about getting those 5 cards and looking at them. So the number of items in the sample space is going to be C of 52, 5. The number of ways to choose or select 5 things out of the set of 52 cards. Now that means that your denominator is going to be C of 52, 5. And by denominator here, I mean the denominator of your probability. That number, which is the number of different 5-card hands that could be given to you at random, is actually 2,598,960. That's big, but just put it there as your denominator. Now, let's figure out the number of ways that you could get the outcome that you want, because the number of ways you get the outcome you want is the numerator in your probability. Well, if you only want black cards, then it means that basically you want to ignore all of the red cards, if that's possible. If you wanted, you could just throw them away or something like that. So what that means then is that the number of hands that we actually want would be the number of ways we could choose 5 cards from the 26 black cards that are in the deck. Remember, there are 26 black cards. There are 13 clubs and 13 spades. And I'm not worried about which of the clubs or spades I get. I'm only worried about the color of the card. So this means that the total number of hands that you might want to have dealt to you, which is the numerator of your probability, is exactly the number of ways to choose 5 of those 26 black cards. And the number of ways to do that is C of 26, 5. Again, it's C for combinations and not P for permutations, because I don't care about the order in which I received the 5 cards. So it's a C26, 5 and as my numerator of this probability. And therefore, my probability is C of 26, 5 divided by C of 52, 5. So that's the probability. Now, if you wanted to actually calculate that, you could, and you'd find after you simplified everything that you'd have 253 divided by 9,996 as your probability. And if you wrote that as a decimal number, it would be about 0.025. Okay, let's move forward then to another example of how we can look at these probabilities related to poker hands that might be dealt to us. So here's the example. What's the probability of having a flush dealt to us at random from a 52-card deck? Now, you might not know what a flush is from a 52-card deck, so let me just share it with you here. A flush is a hand where all 5 cards come from the same suit. So either all 5 cards are hearts, or they're all 5 diamonds, or they're all 5 spades, or they're all 5 clubs. Now, the denominator of this probability is the same as the denominator of the probability in the previous example. It's going to be C of 52, 5, because the sample space is the set of all possible 5-card hands that you could have dealt to you at random from a 52-card deck. So your denominator is C52, 5. Now you need the numerator. And that means we need to understand the number of different ways that we could have a flush dealt to us out of that 52-card deck. Well, the flush then means that I want all the cards to either be hearts, or all diamonds, or all spades, or all clubs. How many ways could that happen? Well, I'm going to suggest that we do this problem using the multiplication principle to help us, and we're going to think about it in 2 stages. First of all, one of these hands that we want, which would be a flush, we would depend on which of the hearts, diamonds, spades, or clubs that we choose. In other words, we can choose one of those 4 suits. And so the first stage in this process would be, let's pick the suit that we're going to come from. And there are 4 choices for that. Now, let's keep that in mind. We'll need a 4 then as part of our final answer. Now, once you've picked that suit, let's say you pick hearts, for example, because you're sentimental, you could put aside the other 3 suits then, leaving you just 13 cards in your hand from which you want to have 5 dealt to you. Those 13 cards would be the 13 hearts that were in the deck. So once you've done that, the number of ways to have 5 hearts dealt to you would be C of 13, 5. In other words, it's the number of ways of picking 5 of the 13 cards which are hearts. And again, I'm not worried about the order in which you hand me the cards. So this is a combinations problem and not a permutations problem. So the number of ways then to have all of the different possible flush hands figured out would be 4 times C of 13, 5. It's a multiplication principle problem. First stage, pick the suit. There are 4 ways to do that. Second stage, once the suit has been chosen, deal out 5 of those 13 cards in that suit. So the numerator of your probability, or what we were calling M earlier, is 4 times C of 13, 5. The denominator, we already said, was C of 52, 5. And therefore your probability is just that ratio, which in this case is going to be 5,148 divided by 2,598,960. And as a decimal, that's 0.00198. And that's not very probable that that sort of thing is going to happen. Now, let's try a couple more of these kinds of examples just to try to nail down this idea. Let's do the following. What's the probability of having a full house dealt to us at random from a 52-card deck? Now, a full house is a very different kind of hand from what we were talking about earlier. A full house means I want to have 3 cards of one kind, like maybe having 3 aces, along with another pair from another kind, like having a pair of 7s, for example. So I want to know, what's the probability of having a full house? Well, in my probability formula, the denominator is still going to be C of 52, 5, because that's the number of ways of having 5 cards randomly given to me out of 52. So now what's the numerator? Well, the numerator is going to be the number of possible full house hands that we can have. Let's figure that out, again, using the multiplication principle. Now, unlike the last example, where I sort of wanted to think of the cards first in suits, you know, a pile of hearts and a pile of spades and a pile of clubs and a pile of diamonds, now I don't want to think of the cards that way because a full house doesn't worry about those kinds of things. I want to think of the cards in little piles. All the 2s, all the 3s, all the 4s, all the 5s, up to all the kings and all the aces, which means I would have 13 little piles in front of me. Now, once I've done that, I then need to think about how I would build a full house from those cards. Well, the answer is to do it in stages. In the first stage, I would pick one of those 13 piles from which I'm going to choose the 3 of a kind. So I have 13 choices for which of the kinds of cards I have in order to pick my 3 of a kind. So I need to remember that 13. That's stage 1. Stage 2 says, now pick one of those 13 piles and put it in your hand. There are 4 cards in that pile now, maybe 4 aces. And now how many different ways could I make a 3 of a kind out of that family of 4 cards? Well, the answer is C of 4, 3. Why is that? You have 4 cards in your hand now, and you want to pick 3 of them. And you don't care which of the 3 out of the 4 you pick. So you now in stage 2 can say that there are 4 different ways to pick your 3 of a kind out of those 4 cards. Now stage 3, go back to the table again, and now you have 12 piles left from which you want to pick the pair, so to speak, that's left in your full house. So you need to pick one of those 12 piles, and you have 12 different ways to pick that pile. So now you have a 12. And now you choose that pile and you ask yourself, out of those 4 cards, maybe you're now holding the 4 7s, how many ways can I give myself a pair of 7s out of these 4 7s? Well, the answer again is a combinations problem. It's C of 4, 2 now, because you want to choose 2 of these 4 cards to make a pair, and that's 6. I now walked you through a 4-stage process for building an arbitrary full house. And now if you think about the multiplication principle, it means that the number of ways you could build that full house would be 13 times the C of 4, 3 times 12 times C of 4, 2. And if you use the formulas we've had for those C functions in the past, that total number is 3,744, which means the probability of having a full house dealt to me at random is 3,744 divided by 2,598,960. Now, let's try to do one last example from these poker hands just to see if we can understand fully how this probability works. So here we go. Find the probability of being dealt a straight from a randomly shuffled deck of 52 cards. Now, let's make sure we understand what a straight is. A straight just is 5 cards in order of their size, if you will. So 2, 3, 4, 5, 6, for example, would be a straight. Or 10, Jack, Queen, King, Ace, for example, would also be a straight. And by the way, Ace, 2, 3, 4, 5 is also an allowable straight. Now, how do we figure out all the total ways to get a straight handed to us or dealt to us at random? Well, the answer is to first start by thinking about what the lowest card is in my straight. Now, how many ways can I pick what the lowest card is? Well, it could be an ace, or a 2, or a 3, or a 4, or a 5, or a 6, or a 7, or an 8, or a 9, or a 10. The 10 is actually the highest of the cards that can serve as the starting point for a straight. You can't start at a jack because then you'd have to go jack, queen, king, ace 2, and that kind of wrapping around is no good. So the starting point for the straight has to either be an ace, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So you actually have 10 choices for where you're going to start building your straight. Now from there, you're going to then have to worry about how to build it after you've chosen that first starting place for this straight. So we're going to build the straight then in the following way. We'll pick our starting kind. There are 10 ways to choose that starting value, if you will. And from there, we're going to then pick the number of ways to choose the cards out of each of those piles. So let's say I start at a 5. I've got 4 5s to choose from, right? And I only want one of them. So there are 4 ways to choose the 5. Then there are 4 ways to choose the 6, 4 ways to choose the 7, 4 ways to choose the 8, and 4 ways to choose the 9. So when I look at that, I realize that the ways to build the straights are the following. Choose the starting value. There are 10 ways to do that. And then there are going to be 4 times 4 times 4 times 4 times 4 ways to pick the actual cards that will be in the straight. And that means that the total number of possible straights is 10 times 4 times 4 times 4 times 4 times 4. So my probability then is that number, 10 times 4 to the 5th, divided by C of 52, 5. And that number is approximately 0.00394. Well, in this lesson, we've discussed a lot of things about probabilities. Some of it's probably scary feeling, and you might have to look at these over and over again just to see what's going on. But I hope you understand from this multiplication principle and combinations and permutations how you can actually build up to these probabilities with relative ease. I really hope you've enjoyed this Algebra 2 course. I really have, and I strongly encourage you to check out the Teaching Company's new pre-calculus course as well as calculus course from Bruce Edwards. And hopefully you'll continue in your mathematical studies and continue to enjoy.